So today I'm going to be talking about reducing blast radius. So I'm hoping that everybody knows about that concept. It's a very old concept. It's been around forever. Can anybody try to explain what it is or tell what it is? Yes, it's minimizing the potential impact of a failure or outage. So that's basically what it is, because we all have incidents, we all have failures, but when you have them, you don't want all your users to be impacted. So this is our journey. I'm going to be talking about what we did at my current company. So today I am the director of engineering at Twingate DevOps SRE. Before I was at Voodoo and IGN, but I've been in this industry also for over 20 years. On this slide, I want to talk about a little bit about our architecture because it's related to what we have done and what I'm going to show. So it's a zero trust network access solution. It's a cloud-based VPN, if you may, but it consists of clients and connectors. So these are almost like VPN gateways, and the clients are your VPN clients. So our control plane is actually what runs like authentication, authorization, etc. And the data plane is where it connects the clients and the connectors and the resources when you want to work on your company's resources. So we're going to be talking about the data plane, the control plane, etc. And I want to talk about why reliability is important, because we run this cloud-based VPN for lots of companies. They're all over the world, so we don't have a downtime. We cannot have a maintenance window and say, okay, we're going to take the system down for an hour. Doesn't exist. It has to be up and running 24/7. We are almost like the internet for them. Okay, so their users, they connect to their resources through our service. And if we are down, they are down. So it's reliability is really crucial. We are almost like a utility provider for them. Okay, so how did this journey started? So before, the reliability was an afterthought, right? It happens when you are small, when you are a startup, and the company was started in 2019, and around late 2021, couple of incidents happened, big incidents. It takes the system down, big outages in couple of months span. What happens is it takes weeks off from everybody's calendars. Executives has to go on apology tours, the account executives, the tech sales, support. Everybody is takes the heat. Customers are all over you. You don't want to be in that boat. And before I start, I also want to go over the tech stack a little bit. So this is our tech stack. Not much change since I used this presentation last December too, I think. We added one more cloud provider. We now use DigitalOcean too, which I'm going to talk about later. But the critical parts are we are on GCP, and we use Django with synchronous workers. So I don't know if you are familiar with that concept, but it's different from Apache or Nginx where you serve websites. But these are synchronous workers that they can only serve one process at a time. And we had great engineering practices and principles. We followed them. We thought, okay, that's enough. Automate everything. We try to automate everything. We had good processes, frequent deploys. We don't wait weeks to deploy something. It's we have multiple deploys in a week. We had all these updates, full test coverages, integration tests, everything you can imagine in a good engineering organization. We had them, and we thought they were enough, but apparently they were not. And just to put again another slide there for the team size, it's about 25 engineers and 3 DevOps engineers. So DevOps to engineering ratio is about 1:8, and SRE is a shared responsibility. So I think a lot of speakers today talk about it. So this is something we have at least were able to implement. Pretty much all the engineers participate in the on-call rotation. They participate in at least fixing them so that they see the problems, and they participate in not only seeing the issues, but also fixing them. So that's, I think, one good thing that we have done. But this also happened after the fact. It wasn't there before. Okay, so when we had the issues, we said, okay, it's go time. Let's do this. Let's fix this. And we did a lot of things on top of just reducing the blast radius. So today I'm going to be talking mostly about reducing blast radius, but it wasn't only reducing blast radius. We did a lot on observability, whether it's on security and different areas, right? But this slide will talk mostly about reducing the blast radius. Okay, so things will go wrong, okay? It's not a matter of if, it's a matter of when. And there are usually two kinds of issues that we've seen. The self-inflicted ones, these are it's like inadequate design or bad rollouts, bugs, everything you can imagine that you are causing these yourself. And there are the third-party inflicted ones too. So these are like not only cloud provider, but also maybe your payment provider or some other third-party providers that you use. And I'll talk about one today that just happened like before this call about 2 hours ago. Luckily, it was localized and we reduced the blast radius that it didn't impact other services. And some numbers, which shows the reliability is actually hard. A lot of teams, they want to do, I'm amazed. So like when we do hiring, sometimes I talk to people and they're like, oh, we are like up 100% of the time. I know it's not true. It's not true for even the big companies with like billions of dollars of budget. It's not cheap. It's not easy. Okay. It's hard and it's costly. 4 nights of outage, it's less than 1 hour of outage in a year and less than 15 minutes, less than 30 minutes in a quarter. So what did we do? We set up a reliability task force. So this meets every 6 weeks. Now, at that time, it was every week, obviously. But now it meets every 6 weeks, identifies and prioritizes reliability projects. And at the time, we defined reliability as a company priority. So it was very important. We defined some goals for the initial baseline goals. And at the time, we said, okay, let's stop the product engineering work for a quarter. Not that much, but it's at least for a quarter. We did that and focused on delivering these like baseline goals for reliability. And my takeaway for this is start early. Don't wait these incidents to happen, okay? Because it gets really hard once the scale grows up, even like today. So I'm going to be talking about what we did on certain areas. And if we had done them, I don't know, like 3 years ago, maybe it could have been much easier. But now our customer size grew, whatever X, and then it's becoming harder and harder. Okay, at the very beginning, I showed the control plane. So that's where the actual backend runs. That does the authentication, authorization, analytics, bunch of different services run there. And before it was on this one single GKE, Google Kubernetes Engine, Kubernetes cluster on one GCP region. So when something happens in that region or in that cluster, boom, everybody is impacted, all the customers. So we said, okay, let's do better than this. And we decided to go with 3. Why? Because we thought, okay, if one goes down, there's still 2 around and it's still not that risky. So we try to like use minimum of 3 replicas when we do things. Sorry. And that's what we did. So we had 3 clusters in 3 regions. The Google load balancer, we use the Google's global load balancer. So it directs customers to the nearest cluster and the backend's running on that cluster. So the customers in Europe, they are hitting the US East one. Asia Pacific, they hit the US West. Somewhere around middle of US, they hit the US Central cluster. And the clusters had to be stateless, right? We had some stateful operations in the clusters. We moved out of them. Everything to database. So database is the only stateful part now. We still have Kafka and Redis running on the cluster, but they are for data that we can afford to lose. That was very critical. And in this design still, we have 2 big single point of failures, the database and the load balancer. So there is no replica of them. Even though Google has replica of them, to us, it's a black box. It's like Google load balancer, but it's one load balancer. Yeah. But on top of that, even though we still had the single point of failures, it allowed us to do a couple of things. All right. Yeah. Okay. So since we had like multiple clusters now, we were able to do safer rollouts. We could roll out to one cluster first and then roll out to the other clusters. Kubernetes upgrades, GKE, they come up with a new version every month or so. So we now do we can take them. It's all automated. We scale down and we kept it simple. So the way it works is that when you scale down the deployments in a cluster, we use something called AutoNet controller that Google has that talks to their load balancer, that syncs your pods and the load balancer. So when you sync your deployments, it takes the traffic away from that zone, from that region. So now you can do all kinds of maintenance on that cluster. So it was simple, and it is just a copy of the same at different sizes because like we saw that US East was getting more traffic, so it's a little bit scale up than the others. And US Central doesn't get that much traffic, so it's more scaled down the others. But in terms of design, it's an exact replica. So it was simple. It's just like multiple regions. And now we are able to do maintenance on these clusters. And we believe in practice makes perfect, because when you build these clusters, you want to be able to rebuild new clusters. If they fail, if you want to spin up another cluster in another region, if you don't test your code, things will break eventually. So every quarter, we build a new cluster. Does it come up, like all the components on it? And we just did one last week, have again data plane and the control plane. The data plane cluster didn't come up. So we found 3 issues that are all caused by recent code changes. So if you don't test building new regions, building new clusters, you're going to find issues when you actually need them. So it's important to test them. And then we also test killing traffic to a region and zone. So these are realities, like cloud providers lose zones and regions. So we basically turn off the machines. Do we survive? If we lose a region, will the other 2 regions survive? We test this on a quarterly basis. Reducing blast radius for database. So it's still a single write database. It's an HA configuration. If it fails, Google will automatically fail to the HA component. It's in the same region though. So it's still like a somewhat single point of failure. But what we did was we split the reads to read replicas. We are using 3 zones in each of the 3 regions that I show you. And each zone got a read replica. So now the pods in that zone talks to the local read replica in that region. And if your system does, 80% reads, you protect the write database, and your system has a bigger chance of staying up when Google has like regional zonal issues. Again, for this one, we added some tests. We test like replica down. If replica goes down, what happens? We adjusted the pods, like there are services running on them that talks to the nearby replica first, but then if it fails, then it automatically switches to the other zones. When the primary is down, if it is not coming up soon, like you have the replica, so you have the option of promoting it to become the new primary, but unless you test it, you cannot confirm it. So this is something, we do all these tests on staging. We don't test it on production. We only do production testing, things like data recovery testing, the data restore testing, but most of these tests happen on staging. Okay, what happens database goes down? This happens not only when the cloud provider has issues, but also every now and then they have a new version. You have to reboot the primary database. You don't want the whole system to go down, okay? So what we did was we introduced something called read-only mode. And in the read-only mode, what happens is, at least for our service, we block the admin operations. Anything you can do via the admin portal or via the APIs, they are blocked off, they are not available, but the rest of the system works fine. What we do is like we fail them safely on the client side or the connector side. If we are down for X number of minutes, there's even like the tokens, they get auto extended. Our tokens are usually like 5-minute durations, but we also pass them 24-hour token. So they fail back to the 24-hour token. Even if the write database is down, the users that are already connected, nothing happens to them. They just work as is. Reducing blast radius for our code. We use a monolith application, even though now we have microservices. Couple of them. We don't do like microservice for every single component. We didn't want to do like hundreds of microservices. So we have the monolith. But with the monolith, we have hundreds of pods running to serve your customers. And when something goes down, everything is impacted. And again, as I mentioned earlier, we use Django with synchronous workers. The problem with synchronous workers is they can only process one request at a time. And each request takes 50 milliseconds, while one worker can do 20 in a second, right? But if the latency goes up from 50 milliseconds to a second because of a third-party dependency, which again happened today, which I'm going to talk very soon, then you need 20x of scaling. okay, from 50 seconds to 1 second. All your pods, they are like busy now, just like waiting on that third party to come back to you. So what we did was we deployed them as different services. So instead of having 150 of the same one backend that is all behind, like serving everything on the load balancer, we said, okay, let's divide them into 30, 30, 30. They are not equally sized, but we divided them into different, what we call services, and they are all split by the URL on the load balancer. So maybe slash API slash auth goes to this backend, slash connector heartbeat goes to this other backend. The hooks, the web hooks, maybe we have like dependency on some third parties, and they go to a different deployment. So they are different deployment, and they are split on the load balancer. We use APM to analyze which one makes sense to split. And then it was very easy to do, actually, because instead of, again, one deployment, you just have 10 deployments now. It's still the same thing, still the same code, and different sizing. It gets a while like to find the right sizing for them, but once you have it, it works perfect. And then this is our APM. Again, we went through them, and then we identified, okay, this talks to database, this talks to this third party, so we split them based on different metrics. And then we added spot nodes and autoscalers, because now we have 3 different clusters. We split the code into 3 different deployments, 10 different deployments. We said, okay, these workloads can benefit from the spot nodes. The spot nodes are the nodes on the cloud providers that can go down and up. Like if they need to take them because somebody is willing to pay more money, they will take all of them. We've seen instances where like Google takes out all the spot instances in a region. So you need to be able to handle that. And out of these like services that I mentioned, some of them could handle that cheaper. It's almost like 1/3 of the cost. And then as you see here, it's also, this is like our weekly, this is 1 week traffic, just like last week, I think. So Saturday, Sunday, Monday, as you see, it goes up and down. And before we couldn't do that. Reducing blast radius for the data plane. Our data plane was already spread out the world. We have 18 clusters. Every time a cluster becomes busy, we put like a nearby cluster. We add another one. So we have actually another one in Netherlands now. They are like independent. And we also came up with a concept of upgrade groups. So since we had 18 of them, we don't upgrade all of them at the same time. We upgrade to 2 first, and then 3, something like that. We have these like waves that to upgrade them. So to protect from the code related outages. But again, this is like one big giant layer. If it goes down, everything is impacted. There's the load balancer, the share, for example. They're all behind one single load balancer. So what we did was we just did multiple of them. They are now at different size. They're at different locations. They have different load balancers. So if load balancer goes down, if you are going to test something on the load balancer, yes, you have like lower environments, but in reality, production, the scale is like much different. You've seen issues like where a change works on lower environments, you take it to prod, it takes you down, right? Multiple data planes, reducing blast radius, it definitely helps in those cases. And then the data planes are sharded by business needs. So now we have a tier on DigitalOcean, for example. It's like much cheaper than running things on Google Cloud. So we run some customers there. It allowed us to use again spot nodes. And then the next is like we want to add fallback logic between them. But this was an easy thing to do because before the clients and connectors connect, they make a request to our API, hey, what's my data plane URL? So instead of this URL, you pass them this other URL or multiple URLs, and then it's not that hard. But when it comes to the control plane, it's a little bit harder, okay? So this was the initial setup. So again, we have these clients and connectors on the internet, the load balancer, start.twingate.com that points to a single load balancer IP. And then we have the clusters, DB replicas, DB here. And then all the API requests they go to customer.twingate.com, okay? And as we have the DNS setup, it goes there. But once you have multiple of them, which I'm going to show in the next slide, we need to have a central database of these URLs to different shards. So we added 2 concepts. We said, okay, shards These are just like you have current production today. We're going to have a replica of it. They're going to call it like shard 1, shard 2, shard 3. And then tiers are a collection of shards. So we can have a European tier, we can have a US tier, we can have a FedRAMP tier. So it's just a collection of shards. So here we decided to use DNS as a shard database. So there are many ways of doing this. We said, okay, DNS is a reliable key value pair, so why not? We just needed the URL to point to somewhere, right? Here, like customer 1 points to shard 1 IP, customer 2 points to shard 2 IP. These are set when these customers sign up. And then they get automatically served by different shards. It's the same for like different tiers. It's just, again, replica set of different shards. So now customers are split across tiers and shards, and all changes are tested on one shard today, okay? And this allowed us to make more significant changes like database migrations. When it's done on production, it can be hectic, but now it's like it can be tested because we have multiple production environments now. And no single point of failure, like the database and load balancer was single point of failure, no longer. Okay, I think last slide. So reliability is hard, we talk about it, and don't make it a responsibility. The reliability, don't make it a responsibility for DevOps SRE teams. It should be shared and make it a priority. The control plane V2 is still under our dev. So we made it only a DevOps problem first. We started early this year, but in the 6 months, we couldn't progress more. So now in the Q3, we made it a company initiative again. So hopefully we're going to be delivering this. And hopefully in the next SRE days, I'm going to share success story or failure story. We'll find out. That's it. So any questions for me?